Section 2.6, Quadric Surfaces. Alright, so for this lesson, I'm swapping the order in which things are introduced and explained through the text. So what is the end of the lesson on your book is what I'm starting off with. So characteristics of common surfaces is a chart that shows you the formula, the equation, and the graph that corresponds to it. Now, don't be too intimidated by these pictures. So this is not like a college algebra class where you're so focused on graphing and precisely showing a sketch of your function where, I don't know, think back of the conic section of your pre-calculus or maybe college algebra, where you were very focused on knowing how everything worked. For these functions, we're mostly worried about just some key points and getting a general sense of what the graph is supposed to look like. So with these sections, or with this chart, and the next chart as well, just take a moment to analyze, maybe make notes about the equations and what equation matches with what picture. So note maybe like, for example, any leading coefficients, or I'm sorry, variables, where if there's a negative sign, and where it is, where it falls in our function, and also the degree of your variables. Now, these figures will vary along, maybe they might be flipped over from left to right, but this is a sense of it. So we first have an ellipsoid, and notice that every degree is to the second power, and we have x, y, and z represented, and it's also equal to 1. We have a hyperboloid on one sheet. Notice we have a minus, one minus separating two terms. We have a hyperboloid of two sheets. Notice there's two minus signs. We have an elliptic cone. Notice one sign and that it's equal to 0. We also have the elliptic paraboloid. Notice our one variable is to the first power, the rest are squared. We have a hyperbolic paraboloid. Notice the minus and the one variable, 1 degree variable. This one in the class, it's often referred to as a saddle. All right, so my suggestion here is just take a moment to identify the key characteristics that we took the time to highlight for each equation, such as where the negative sign is, what values are squared, which are not squared. All of the equations above come to be formed from the general equation of quadric surfaces, and the absence of some coefficients, meaning the coefficient being 0 and grouping your copies of your variables, which will lead you to also completing the square, they all stem from this general equation of quadric surfaces. So your definition is quadric surfaces are graphs of equations that can be expressed in the form ax squared plus by squared plus cz squared plus dxy plus exy plus fyz plus gx plus hy plus jz plus k equals 0. And all of the equations we saw above can be written in that form if we multiply them out so that there aren't any fractions, and if there's missing a variable, then we just put a 0 coefficient. So they all come from that general quadric surfaces. Okay, so that's the end of the lesson once we develop these ideas. But really, there isn't too much to develop because we're not going too in detail in graphing and creating a perfect sketch of our function. We're not doing it, your text isn't telling you to do it. We're mostly trying to become familiar with how these shapes are and just key points for when we move on to the features such as integration, we know our bounds within these functions. So this was the beginning of your lesson. Identifying cylinders. We often encounter cylinders as straws or a soda can, but in math, we use it a bit differently. So this is our definition of a cylinder. A definition of a cylinder is a set of parallel lines, or lines parallel to a given line passing through a given curve, such as a cylindrical surface or a cylinder. The parallel lines are called rulings. So as we look at this picture, so here we have the graph of x squared plus y squared equals 9 in the third dimension. And if you look closely, all these lines that are parallel to one another that are on the surface, that's what defines this as a cylinder. The collection of these lines along some curve of surface is how we define a cylinder. And these parallel lines are called rulings. And if you look at the beginning pictures, you can also see all these rulings along our functions. That's just a characteristic, so just know how it's defined and what it is. Also, notice we have a circle, but here it looks more like a can of soup, right? So what's happening is the absence of that variable, in this case, the absence of the z variable, makes it so the z variable, every z is true in the function. So it extends for all of the z's. Actually, it continues on to infinity. This is just a chunk of our graph. Every z value that it corresponds to that can be applied takes the value that's there. So really, this is a never-ending cylinder going up and down. A never-ending tube, I guess you can say. So the absence of it makes it so it extends on forever. Consider the rulings in the image above. Plane shape with a generic curve with parallel lines with another fixed line. So that's your rulings. Let's do an example. So again, I'm not being hypercritical of the graph. I just want us to get an idea of what we're looking at. So now we want to sketch the graph of the falling cylindrical surface. Well, here we have it. We know from our graph, we have a plus equal to some radius squared. We know it's a circle, but it's along the x and z plane. So our y plane extends on forever. It takes on every y along its path. Now, how can we develop our, I guess we could say, our third dimensional image when we're not focusing on the graph itself? Well, what we can do is we can graph what's called a trace. So traces, as we move forward, so when sketching a surface, we will see that it's useful to sketch the intersection of the surface with a plane parallel to one of the coordinates. These curves are called traces. So for example, here's a function, I think, here it is. It's z equals sine of x. Well, we know working with that z kind of makes it weird, but we know how to graph sine of x, right? So we can go ahead and graph our sine of x function, just as we see here, and just make a correction to our dimensions. So we usually use x and y, but we're given a z, so we'll use x and z. And I can make that 2D graph that you've worked with in the past. And from there, I can expand it to that third dimension image like we have to the left, where that y plane extends on forever. So we see that y goes on forever. Think of it as like a paper, right? That's the image we see here. So that two-dimensional graph is what's called a trace. It lets us figure out and point out these key points in our graphs. Definition of traces. The trace of a surface are the cross-sections created when the surface intersects a plane parallel to one of the coordinate planes. I like to think of this as working with 2 dimensions at a time, 2 variables at a time. Let's do an example. Sketch the ellipsoid x squared over 2y, not 2y. Let me start again. X squared plus 2 squared plus y squared over 3 squared plus z squared over 5 squared equals 1. Begin by sketching the traces. So here I have the traces. Now, what is each trace? So we see here that first graph is, we see an x and a y, so we're only working with our x and y variables. That z variable is, I'm not sure if it's correct to say it, but it's gone. So that term with the z, disregarded. So we have x squared plus 2 squared plus y squared over 3 squared, and let's disregard the z term, equals 1. So here we see that our x-axis, which runs from left to right, has a term of 2, so it goes from left to right 2. That y-axis, which we're making it run up and down, has a term of 3, so we go up and down 3. And we see how since it's centered at the origin, we're going up and down 3 units and left to right 2 units, just like we would in ellipse. Let's take a look at another function. In another function of the trace, we're working only with the x and the z, so we're disregarding the y, so that we have x squared plus 2 squared plus, we're disregarding the y, we have z squared over 5 squared equals 1. And this gives us our function. Our x-axis goes left to right 2, just as our denominator says, and our z-axis, which runs up and down, goes up and down 5 units, since it's centered at the origin. And of course, our third trace, which has only the z and y variables, would be made up of, so no x, y squared over 3 squared plus z squared over 5 squared equals 1. So here we see the trace of a function. We see our y goes left to right 3 units, and our z goes up and down 5 units. So these are called our traces, or our trace. Now, if we combine these together, think of them as interlinking into our x, y, z coordinate, then we're left with this image below. Here we see our traces interlinking to one another, right? And what is our end result? That ellipsoid. Now again, this would be super hard to draw by hand. Maybe if you're using a calculator, it wouldn't be so bad, or some type of software. So that's why I'm saying, don't worry too much about the graphing. Just understand where they come from and recognize the function. One of the other images we'll see is an elliptic paraboloid. So what makes this different from the one we saw is that the one above was made up of 3 cylinders, not cylinders, 3 ellipses, while a 3D function doesn't have to be made up of the same type of conic. It can also be made up of other functions. And this is what makes this elliptic paraboloid different. If we look at this, it's made up of a cylinder, not a cylinder, of an ellipse. Right here we have an ellipse, but it's made up of 2 different parabolas. We have this wider parabola here, but if you were to turn it over, we have this skinny front of the parabola here. And I'm so glad I have this image with me. It would be so hard to do this on a chalkboard or a whiteboard. So here we're considering 3 different graphs, a parabola, another parabola, and an ellipse. So we have this graph. So this is our elliptic paraboloid. It's our definition above. Let's do this example. Describe the traces of the elliptic paraboloid x squared plus y squared over 2 squared equals z squared over 5. Okay, so we have our answer and we have our traces. Let's go ahead and see how they come to be. So we know that this result answer is made up of our three traces interlinking and seeing what we have. All right, so we have this first trace working with our x and our y. Let's disregard the z. So we have x squared plus y squared over 2 squared, and let's disregard the z to create our ellipse. Okay, so we see that we have an ellipse center at the origin with my x-axis going left and right 1 and my y-coordinates going up and down 2. We have our ellipse. Then we have another coordinate. Let's disregard a variable. So when you're graphing, it seems as though you always have your x-axis going left to right, both when your y goes up and down and your z goes up and down. But the moment you throw out that x, we have z going up and down and y going left to right. Okay, so our other option is working with y and x. If we work with y and x only, we have our graph x squared is equal to, or plus, y squared is over 2 squared is equal to to 0 in a sense. So we can write this to be oh no, I think this is wrong because we already did x and y. These axes are wrong. So this would be my, give me a moment. We have x squared is equal to z over 5. So we have x and this should be z. So here we have our parabola and this would be x and y. If we had x and y, this would be y squared over 2 squared is equal to z over 5. Now we have x and y, x and z, and y and z. There we go. This should be a y. So there we have our two parabolas and our ellipse. If we put them together, we can see we have this elliptic paraboloid. We know we have this by interlinking our three traces. All right, so for your homework, you have problems 313 to 329 odd, and your problems are not making you graph. Rather, they're making you identify a function to the given quadratic function, and that is based on identifying the equation. And your other set of problems are writing them in standard form. So if you're not too comfortable, maybe you might want to review completing the square. Because if there's two copies of a function, or I'm sorry, two copies of a variable, you want to make sure you write them as that single variable squared. All right, so that's it for section 2.6. Thank you.